Welcome to today's webinar, DreamHost Case Study, DreamObjects with Ceph. I'm Danielle Wumble, Director of Marketing at Inktank, and your moderator and webinar organizer. Before we start, let's take a moment to ensure that everyone is familiar with the webinar control panel. At the top of the slide panel, you will find 4 buttons. These buttons can be used to ask a question, answer voting questions, view attachments, and additional related material. You will also be able to rate the webinar and leave us feedback. Please feel free at any time during the webinar to ask questions and to leave feedback, as these are important to us. I would also like to note that today's webinar will be recorded for future playback. Thank you for joining our 3rd webinar, which is part of a webinar series that we will be closing out next week. Today's webinar will feature expert Kyle Bader, Senior Systems Engineer at DreamHost. Kyle will provide an overview of their multi-terabyte implementation of Ceph and why they chose Ceph. Now I'd like to turn it over to Kyle.
Hi everyone, I'm Kyle, System Engineer over at DreamHost. I've been with DreamHost since about 2007. Right now I'm the Systems Lead for DreamObjects, and it's been an exciting adventure. I'm really interested in storage, distributed systems, networking, Linux internals, monitoring, all those OPSI kind of things, with a particular focus on networking and storage. I built my first Ceph cluster 2010. We took a handful of old Core RAID shelves, 13 drives, 5 to 6 pizza boxes, and we created the Ceph playground, and ever since then we've been, making bigger and better Ceph clusters. So I've been experimenting with it for a while. So today I'm going to talk a little bit about the anatomy of DreamObjects, or DreamHost's cloud storage service. I'll be going through hardware, go through some of the ways we did the networking, Ceph-specific details, and then also a little bit about how we control and manage the systems. So first off, we have our Ceph storage nodes. On those, we're running, we're not running the most cutting-edge processors, but it's enough to get the job done as far as Ceph is concerned. You remember that with Ceph, your storage nodes are actually intelligent, and they're actually participating in the redistribution and remapping of data. So you do want a little bit of horsepower there. We usually run about 32 gigs of RAM. We initially were using less, but we decided that we wanted at least 2 gigs of RAM per OSD, partly so that you have plenty of disk cache, so that things are nice and fast. But also, when you're doing some big recovery operations, as the OSDs work with each other to figure out how to redistribute the data, it's better to have more space than less, so that you don't run into problems with running out of memory on your OSD daemons and losing them and then causing more recovery. Right now we're using LSI Mega RAID controllers, and we have a whole bunch of network interfaces. So we're running 5 gigabit links, 2 of them bonded for the front end, which is the Rados network, and 2 of them bonded for the back end network, which is for the cluster remapping and recovery. And then for out-of-band management, we use IPMI 2.0. In future deployments, we'll definitely be switching over to using 10 gig Ethernet. Some of our newer clusters are designed that way. It's a lot simpler. We also have support nodes, so we're running Intel Westmere. It's not the most cutting edge, and they're not the Sandy Bridges, but they get the job done. We're running about 8 gigs of RAM in each, multiple gigabit Ethernet interfaces on those, and we usually run about 4 SAS drives, making 2 mirrored volumes. We use these nodes for Ceph monitors, Rados Gateway application nodes, proxies, and object sync service. So on the networking front, we decided to go IPv6 native with everything. The reason why we decided to go with IPv6 is we don't want to have to go through multiple migrations. You know, for a big project that's a cloud object store, we don't have to put our customer. We don't want to put our customers through the disruptive transition phases as we move from something that's more V4 specific into IPv6 native. So to make that work, we do dual stack application proxies in front of our RESTful Rados gateways, and then they listen to IPv4, IPv6 on the front, and then they're able to talk to the back end. That's all IPv6. Again, everything is 1 gig links bonded, front and back links, and we use a lot of LLDP for discovery. It makes managing the bonded links a lot easier. Again, our newer stuff is using 10 gig. It uses more of a fat tree topology. We're finding that it's a lot easier to manage than having to deal with all the smaller size bonded links. Iterating over this a little bit more, our application proxies, we use STUD for SSL termination and HA proxy for load balancing. We let our routers do the work as far as splitting traffic among them, and then those are all 10 gig front and back end. So this is probably what you guys have been excited to hear about. I wanted to talk a little bit about the Ceph specific parts of DreamObjects, which is pretty much what the product is comprised of. So right now we have 2+ petabytes of raw storage. We use triplicate replication. We have a little over 900 OSDs in our production object store cluster. We've calculated it out to 7 nines of durability. We did that using Inktank. Actually has written some great modeling tools, and they have the source available on GitHub under their Ceph tools repository. And then you can calculate things based on the number of the replication factor you're using, the disk mean time before failure. We factored in some of the information from the Google FAST paper they released in 2007 to kind of bring the manufacturer's mean time before failure numbers a little bit closer to what we actually think we're going to see. And then that's where we came with the 7 nines durability. Now, we're still in a single data center, so anything greater than 7 nines of durability is not really relevant because at that point, it's more likely that there's going to be a regional disaster than you're going to, than you would lose the data, by other means. So that's what we're looking to do in the future is multi-data center to increase the durability beyond 7 nines. So one of the key parts of Ceph is the crush algorithm, and that deals with the original placement and remapped placement of data within your cluster. So we've tuned our crush configuration so that it is rack, row, and node and disk fault tolerant. That means that we can lose any disk, we can lose any node, we can lose a whole rack, and we can lose a whole row, and it will not affect availability of our cluster. We tested it, and basically what we did was we created a large synthetic load, pushed it against the cluster. While we were pushing the synthetic load, we did all those things. We took a row down, we took a rack down, we took nodes down, we took them, we contracted the cluster, in those increments, and we expanded the cluster back in those increments. And in the process of doing each, Crush does all the heavy lifting of having to redistribute the data, making sure that you still have the replication factor despite your cluster shrinking, or when you expand, making sure that you have optimal placement and things are levelly level distribution of your data. We've also had to do online expansion and contraction in production. Nodes die, disks die. You have to contract and expand the cluster. If you do it carefully with weights, you're able to do it without affecting availability. Bobtail is even better at doing this. Our objects are striped, so larger objects will be striped across multiple OSDs because of Ceph's, because of the design tenet of Ceph. The intelligence is pushed down to the object storage devices, so you're really able to distribute the load across them, and then pull in all these different fragments of a large object, assemble them, and then serve them to a client quickly. For our OSD configuration, we chose to use hardware RAID. We configure them as single disk RAID zeros because our controller does not support a JDAVON mode. We put 2 partitions on the RAID 0 volume, a smaller one for the journal, and then the large one for data. We always enable write back on our RAID controllers. It tends to speed things up a bit. And we found that it is best to disable this cache. We don't want there to be too many different levels of caching, and we found that it was a good reliability performance trade-off. We use XFS for the file system. Butterfs works well and it's faster, but we found XFS to be more consistent, at least when we did a lot of heavy testing 6 months ago, and we've been sticking with XFS since then. But we are evaluating Butterfs still because it is significantly faster. Application tuning. So we have the Rados Gateway nodes. We run them as under FastCGI with Apache. We configure the Apache not to handle keep alives. Our keep alives are handled up at our load balancing layer with HA proxy. We had to increase our Apache and Rados Gateway thread pool so that we're able to process requests for many clients. And we've also had to raise the U-limit for file descriptors on the Rados Gateway so that we don't run into any bottlenecks. And so far, that's most of the tuning we've had to do. A little bit of kernel tuning and stuff to eke a little bit more performance out. Right now, our production cluster is running the Argonaut release of Ceph. We have done lots of failure testing. So the large-scale failure testing, where we were taking down rows and racks and nodes and everything. We were turning switches off, and it works incredibly well. It's actually pretty amazing the way that you can go and you can turn off the switch or turn off the power for an entire rack of servers, and things just keep chugging along. The first time I saw it, first time we saw it working, it was pretty cool. Pretty cool stuff. With Argonaut, we found that when you're expanding and contracting the cluster, if you want to avoid disruptions, you'll want to slowly weight in and weight out the OSDs from the cluster. So they're weighted between 0 and 1. So we usually do it in 1/10 increments as we move new OSDs in, and that tends to make it so that the reshuffling and remapping and recovery of data is doesn't end up starving legitimate Rados client requests. So Bobtail. Bobtail addresses a lot of the, makes it so that you don't have to wait in and wait out OSDs when you're expanding and contracting. There's some tunables to make that less aggressive, which you'll want to adjust depending on the size of your cluster. It also brings a couple features that we want to see in our next iteration of our object store. So add CNAME support, and then OSD performance in Bobtail is much better. Mark Nelson from Inktank has done an excellent job of gathering doing a bunch of benchmarking and performance tuning for various RAID controllers, RAID configurations, file systems, and the two different releases of Ceph, Argonaut and Bobtail. You can dig through the Inktank blog if you want to go back and see that information. I suggest do that if they're serious about building a Ceph cluster. Now that I've talked a little bit about Ceph, I'm going to talk a little bit how we manage our cluster. So we use a number of open source tools. That's kind of our motto over here at DreamHost. We want to use things that are open so that we have the visibility and we have the ability to make them better or adapt them to suit our environment. Most of the heavy lifting is done with Ceph. Using Ceph to configure Ceph and talking about it definitely twists up my tongue and fingers far too frequently. We use Ceph to bootstrap the cluster. We do bare metal deployments of new nodes, and then from there, Ceph pretty much handles everything else. Packages, configurations. We kind of have a declarative. Our versions of our Ceph cookbooks are more declarative. So you declarative the state that you want the OSDs to go into, whether you want it to have them be created, destroyed, you want to switch them over to be encrypted. And so that's what we have right now, and it seems to be working well. On next convergence, it goes ahead to see if there's any state changes for OSDs, and then we'll actually make that happen. We search for node metadata through Ceph using the RESTful API, and then we're able to assign the unicast addresses for the Ceph monitors to all the nodes by just doing a simple search. Those are user SSH key management, everything, soup to nuts. We use PDSH to kind of do offhand information gathering from the cluster, or kind of run one-off tasks, and, to check things, or flip a bit easily. If we want to collect a bunch of information about all sorts of things. So PDSH is great because what we do is we have Ceph create the genders files. Put on PDSH it kind of acts as a cache of the nodes that are in your architecture, because that information is discovered, given to Ceph, and then pushed down as a file that stays there. So PDSH works even when the Ceph API isn't, which is handy if you're having interesting network partitions or whatever stuff happens, and it's great to be able to get around to all your nodes in case you need to. We use a little bit of Run It, and we use a little bit of Upstart. Upstart is the development of the Inktank work is moving more in the Upstart direction, so we're adopting some of our stuff over to Upstart, but both, the principle is the same. You want to use some sort of process supervision to make sure that things stay up. We run right now, our OSDs on our object storage cluster are still not under process supervision, but they don't die too frequently, so it turns out to work well. And when they do die, we don't want to kind of mask that behavior. We want to go and figure out what went on and make things better. We are a big fan of kind of like continuous improvement, continuous delivery. So we have continuous API functional tests that are running against our development, our staging, and our live production cluster. We also use it to monitor Ceph convergence, and it generates alerts on failure that go to our paging system. So it is probably the single best indicator of when there's a problem, because it exercises all the API functionality, make sure everything is working how it's supposed to be, and it's a really high level type thing. And then, later, if we see it, we can dive down and dig into the issue. To help dig into the issue, we use a relatively new monitoring system, kind of like for people that have used Nagios and are looking for something a little bit more modern. Open source, written in Ruby. It stores state in Redis. It uses kind of like a pub sub architecture for collecting alerts from or collecting state from a local agent on the machines, and then you can write handlers that then watch system state and then can generate alerts. If it meets certain criteria. So we use Sensu more as a dashboard that, once we know that there's problems, we go and look and we can see it does kind of component level monitoring of, different daemons that are in our system, at our load balancers, at the Redis gateways, at the OSDs, et cetera. We run collect the agent on all of our machines to collect a bunch of system metrics. We also use Diamond, which is a Python metrics collector for getting metrics out of the Ceph performance sockets. So then you can get a little bit more data from Ceph to send up to your metrics platform. We use Graphite. It's really fantastic for storing metrics. We've used both, RRD tool type stuff, but Graphite really stands apart because of it's really kind of the way it writes metrics out sequentially, makes, as opposed to RRD, which is a lot of random write. It seems to support a lot bigger load of metrics going towards it, and also the graphing dashboard is really great for being able to, we build a bunch of dashboards and then, we can click through them and look at all the monitors, look at all the Redis gateways, look at all the different layers of the network and, watch the throughput on them and different nodes and stuff. So it's been incredibly valuable at diagnosing issues and also going back and figuring out why things happened. For log management, we use Logstash. We run a client written in C called Lumberjack that goes ahead and pulls up the logs, sends them off to a Logstash server. The Logstash server we have set up with a Graphite and Elasticsearch output. Elasticsearch then exposes a RESTful API that we can use to query and find out more, really dig into our logs. And then we have Kibana web UI that sits on top of Elasticsearch. So that's really cool stuff. In the future, we're looking to, maybe add another region on the East Coast. We're looking at a pool replication. There's a bunch of stuff we're looking at doing on the horizon. We're still deciding which order we want to do things in. So, there's definitely a lot of exciting stuff going on. We're going to continue to iterate and make DreamObjects better. So that's it for me. At this point, I'd like to ask if anyone out there has any questions they'd like to ask me. And then there's also my contact information if someone thinks of something later and they want to get a little bit more.
Great. Thank you, Kyle. So we do have a question, and if anyone else has any questions, you can use the question button that's on the top of the screen to enter your question. The question is, have you compared XFS ODS to ext4?
So we haven't, back when we were looking at different file, we did kind of a file system bake-off where we had a single cluster, and then inside the cluster we actually ran 3 different file systems. So we tried to run ext4, XFS, and Btrfs, and at the time we did that testing, I don't think that ext4 had sufficient extended attribute support for us to do what we needed to do. I could be wrong. I could follow up and find out the exact details, but we did look into doing it. There was a reason why we couldn't, and I don't think that still holds true. So I think Mark may have some information. We can definitely follow up on that. I see another question on the performance of Zen compared to KVM. My side hasn't done a lot of testing on the different hypervisor. I've been more focused on the Rados gateway with this product, but we could definitely probably get some information on the difference between the different hypervisors when you're using a Rados block device. So, yeah, we could follow up on that. Next question I see is what is the normal bandwidth that a Ceph cluster is providing to the servers? So in our current architecture, we have the Ceph cluster, which we have, the bonded front and back 1 gig network interfaces. And then our clients have 1 gig on the front end for application traffic, and then we have one on the back end to talk to Ceph, and we're easily able to saturate and get full bandwidth through that machine, if that answers your question. Next question is, do we run storage SSDs or we run nodes with no SSD journals? Doesn't that hurt performance? Yes. Things are going to be more performant if you use SSDs for your journals. We were worried about durability with SSDs because the journal is pretty active, especially when you're doing a lot of remapping. We were worried about burning through them. It would be interesting to try it using some of the more recent SLC technology that I think has more writes available to it. But yeah, it's something that's definitely on our radar. We haven't done it yet just because we're not confident in not having to end up replacing them, every 6 months. The next question is why didn't they use Swift? Well, Swift is the OpenStack version of way to provide object storage service. Honestly, we were experimenting with using Ceph to power our object store before we really knew or had heard much about Swift. So this is something that we've been working on for a long time. It's a different architecture with Swift. It's more of a dynamo ring approach as opposed to using Crush. So there's the way it distributes data is a little bit different. That said, we support the Swift API and the S3 API. Is anyone else out there?
Thank you, Kyle, and thank you for all the great questions. We will follow up in the next few days with everyone. So I'd just like to talk about Inktank's professional services for a few minutes. We do offer consulting services and support subscriptions, and a full description can be found at the link below. And you can also just go to inktank.com to find everything. Check out our upcoming webinar and our on-demand webinars. You can go to the Inktank website, and there's actually a link right on our homepage to these. And you can watch them all right on our homepage. And next week we have the advanced features of Ceph distributed storage, and Sage Weil, our creator of Ceph, will be presenting. That's on Tuesday. And also, this webinar will also be available shortly for replay. I'd just like to ask a couple of voting questions, and then after this, I noticed that we do have 2 more questions that came in that we will ask as well. For the first voting question is, what is your biggest storage challenges? We'll give you a few seconds for you to answer those. All right, the next question is, what additional information would you like to learn about Ceph? And finally, which components of Ceph are you using today? Great, thank you. Kyle, would you like to go back to the next question?
Absolutely. So the next question that came in was how much storage per storage node? I had mentioned 8 to 12 OCs per server. They were curious if I was using 2 or 3 terabyte disks. In our current object store, we're using 2 terabyte disks. In our newer cluster that we're standing up that is roughly the same size as the DreamObjects cluster, we're using 3 terabyte disks. So yeah, answers both. And then the next question is, what's the least amount of nodes for reasonable performance storage for hosting VMs? I'd probably have to defer to one of my colleagues who's been doing more work on our compute project. He would have better information as to the performance for the VMs. I've been more focused on the S3 and Swift compatible APIs for object storage. So we can get that information. I don't have it readily available.
Great, thank you. So finally, you can contact Inktank at info@inktank.com. And also don't forget to follow us on Twitter, Facebook, and YouTube. And one final note, the actual presentation slides are available under the attachment button. Also, in a few days, we will be sending out a copy of the DreamHost Dream Compute Architecture Blueprint, which will also be available on www.inktank.com. Thank you very much.